All right. So everybody can see that okay?
Yes.
Okay. So welcome to High Level Design to Silicon Reality, how Rise and Precision can accelerate AI-guided exploration. So there's a lot of different webinars that we have online. So this isn't going to be an introduction to HLS or all those other things. Those are available from Rise if you'd like to get that, and you'll get access to all of those. So today's speakers, I want to do a quick introduction of today's speakers. So first off, we'll have Mike Fingeroff, who's Chief of High-Level Synthesis with over 20 years of experience in hardware design. Mike has specialized in high-level synthesis, focusing on machine learning and early performance modeling using System Verilog, System C, and MATLAB. He's the author of High-Level Synthesis Blue Book, and his expertise includes C++, System C, and video and wireless algorithms. And then next up, we'll have our guest speaker, Tom Spyru, who is the CEO of Precision Innovation, the primary industrial developer for the OpenROAD EDA tool suite. Tom is a well-known EDA system architect, and before his current position, Tom has worked for over 30 years as an EDA technologist and has gained extensive experience in areas including static timing, logic synthesis, power grid analysis, data technology, floor planning. He has led the development of leading-edge commercial engines products such as Primetime, Voltage Storm, First Encounter, and the Open Access Database. He's a key architect of timing closure in the Altera Cortex FPGA tools, and Tom has been driving EDA algorithms to utilize parallel programming approaches with both multi-process and multi-threaded techniques. And then after that, we will have Alan Klink, co-founder of Rise EDA and technology leader with expertise in high-level design and AI and ML frameworks for verification. He has driven innovation in verification, low-power technologies, and helping teams enhance efficiency and performance in modern complex design. So we've got three great, very technical speakers coming up today. So here's our agenda. Again, we're going to start off, I'm going to give you a brief introduction, and then we're going to jump over to Mike to help you understand, well, what can you do with HLS and architectural exploration with the RISE toolchain. Then we'll bring it over to Tom to talk about physical estimation and correlation with OpenROAD and precision, and bringing it all together with our AI solution with Alan Klink and the live demonstration. Okay, so I'll give you a quick introduction on the RISE side, who we are. So we are focusing on delivering implementable, verifiable, high-quality RTL that is practical and we can do today. So founded in late 2022, veteran EDA folks, we all got a little bit of gray hair from decades of experience in EDA, officially launched in 2024. So we're a fairly new company with 10 employees based here in the United States. Essentially, what we do is we are bridging the gap between architecture and design, and you're going to see that a lot today in the architectural exploration. So be able to go from using, have your software and your architecture and how you can bridge that in with the silicon. And we start with a high-level design that is written in System C or System Verilog or C++. And you can model and analyze the system performance. We've got different levels of abstraction that can be synthesized. And then using that RAISE abstraction in that language, we have a complete tool chain and platform that will deliver high quality, high Q of R, which we'll focus on today, RTL, and then using specialized high-level agents not only to help you understand the code, but today we'll show you specifics about how it will help you do the exploration. But the results from the RISE toolchain is synthesizable high quality, basically high PPA, the PPA that you're targeting, RTL. The products that we have here at RISE, I think if you've been to a webinar before, so that we've probably seen this slide before. Again, we are industry first for being able to do high-level system Verilog, and there's some other webinars that we've talked about what exactly that looks like and how you write that system Verilog, and C++ and System C. So any of those languages with the whole platform, turning that into high-quality RTL. We have a set of generative AI advisors and agents, multiple levels of synthesis, which enables us to get that Q of R. Mike will talk a little bit about some of that today that enables us to get such high Q of R. a high-level verification solution, which we have done a previous webinar, and a full debug and analysis that lets you completely trace the code from high level down into RTL, be able to understand exactly what the tool has done as it's moved between those levels of abstraction. Okay, so let's talk a little bit about exploration. So I'm not really going to dive into any more about what HL is and the RISE platforms. There's a lot of info out there, or you can get some questions. I want to talk about HLS in its past has enabled some levels of design exploration, but these are the kinds of things that are just not feasible with hand-coded RTL, right? So within a high-level synthesis solution for exploration, you can get tens, if not hundreds, of different RTL solutions very, very quickly, and Mike will talk about that. We've seen multiple customers that have discovered unique architectures that they actually couldn't do or couldn't try with hand-coded RTL because you just don't have time to rewrite and try all of that stuff. And it really enables you to do very early what-if analysis. What if I did this? What if I tried this architecture? What if I did this? Is it implementable? What does the RTL look like? What kind of timing can I get, right? So it really enables you to try all these different things quickly and confirm if those architectures will truly meet your PPA, not by just spreadsheets, but by actually generating the RTL and running it through simulation, running it through your tools and seeing if it will actually really meet it. The challenges with some of this is that the execution can take a long time and be a lot of compute. A lot of times we've seen that HLS, the PPA prediction that we come up with for what the timing and the area of the RTL will be doesn't actually match the silicon. And so Mike will talk a lot about that and how we've addressed that at RISE. And small high-level changes can sometimes result in large Q of R swings. And so if you're familiar with high-level synthesis, sometimes little tweaks here and there can make a huge difference, and you need to be able to understand that. So you need to overcome these challenges. And then lastly, physical design problems. So is it routable? Is there going to be problems? Are you going to get extra timing? Are there going to be all sorts of issues as you try to take that RTL down into the physical design tools? So you need to get that feedback. So what you need is really high correlation for Q of R. So you need the numbers that are coming out as you're doing this exploration to basically be matching very closely to your production level RTL synthesis tool, and your PNR tools need to match your production level PNR. But you need very, very fast run times, and we'll talk about that. A license model that enables hundreds, if not thousands of runs so that you can scale this across your AI ML infrastructure, and an AI in the loop to really basically speed decision processing. So what we've done together with RISE and Precision is really enable this solution to go from high-level design all the way through estimation and physical implementation to be able to get that kind of feedback in order to make these kind of decisions. So finding optimal RTL reliably and efficiently with the boosted confidence that you have the physical implementation feedback that this new architecture is actually achievable. Very fast runtimes, so 100 to 1,000x faster than traditional tools for RISE, and Precision 40 to 20x faster than proprietary tools. And most importantly, excellent correlation. For the RISE set, highly correlated to production level synthesis, which Mike will talk about today, and Tom will talk about the physically aware RTL choice and the correlation to place and route. Metrics-driven toolchain and AI solution, which Alan will talk a lot more about. You need to have things as you're making these decisions grounded in the tool chain. The tool chain needs to be feeding back into the AI solution. So you need to have that iterative path and metrics-based decisions for your AI. And then again, a license model that enables the scaling. So RISE has an unlimited per project license model, and Precision has a productization cost that both we'll talk about. Okay. I will stop with the introduction. Again, we can add a question and then turn it over to Mike.
All right. Thank you very much, Ellie. Again, just to reiterate what Ellie talked about when we started, if you have any questions, feel free to type them into the Q&A, and we will answer them either directly in the Q&A or answer them live. This is a very short overview of high-level synthesis because if you want to see more details, there are plenty of webinar videos that we can point you to from our website. But this is just to kind of set the stage for talking about the back-end tools. Um, and ultimately, this is a high-level design flow, but we're generating RTL. So what does high-level synthesis do? And that's just one small piece of this whole flow, but a very important one is that it converts untimed or loosely timed System Verilog, C++, or System C into synthesizable RTL. So the output of our HLS flow is synthesizable RTL that's going to go into the downstream tools. Um, what it's really doing is it's automating a lot of the low-level things that an RTL designer would have to do. So for one of the big features is it's going to automatically insert pipeline registers into the generated RTL to meet the user's clock frequency constraints. And what this means then is that you have technology independent source because now you're just simply implementing the functionality and the architecture and not worrying about the low level microarchitecture. It adds data flow control. So you can design using these streaming channel interfaces in the various languages. And these essentially are interfaces that have a point-to-point protocol. So you have a data ready valid protocol, and that protocol is what's used to control the data flow through the pipeline. So you don't have to worry about managing data flow. It's all happening transparently. You get to explore parallelism by turning the knobs for loop unrolling. And this allows you to trade off area of performance and power. And this is one of the knobs we'll show you as part of the demo without getting into all the nitty-gritty details of HLS. And then another very powerful feature is typically in modern hardware, you're going to need memories to store data locally. And HLS is able to infer memories from arrays in either your System C or System Verilog design. And that means it's going to generate all the address data and control to be able to hook up to that memory, which again is just low level work that if you don't have to do it, you can just design much faster. Um, so with high-level synthesis, you get to do what's called architectural exploration. And so doing this, from a single high-level design description, you can generate many different microarchitectures with different power performance and area trade-offs. Some of the common knobs, and the one we'll look at today is loop unrolling. So unlike low-level RTL languages where you can have loops, but they're automatically unrolled and implemented in parallel, as a user, you get to decide how much of a loop should be executed in parallel. So you're really controlling the number of operator level operations. You get to explore memory architecture, so you can automatically change memory bandwidth. You can create bank memories, different various implementations. Again, because memories are inferred, you're able to do this very quickly. And you can also explore interconnect architecture. So um, along with the standard streaming channel interfaces, we support higher level interfaces like AXI, and you can quickly, change your data bus widths and explore the effects of that added bandwidth in your entire system. Just to give you an idea about the one knob that's one of the more commonly used ones in high-level synthesis, and this is what we'll demonstrate, is loop unrolling, as I mentioned, allows you to control parallelism. And so depending on your design requirements, you get to decide how many operators or operations you need to have happen in parallel. And that's as simple as specifying a constraint in the tool. So one of the differences between high-level synthesis and System Verilog is that, as I mentioned, in System Verilog, loops are always going to be unwound fully and executed in parallel. Whereas in high-level synthesis, I can say, don't unroll a loop. And now this particular multiply accumulate operation is going to do a multiply every clock cycle and a single accumulation. And so the hardware you get is a shared multiplier across all these different array elements. So it's very small, but it's also going to be slower in performance because it's going to take words, a number of clock cycles for this piece of hardware to execute. Um, I don't have to fully unroll. So the nice thing is I can say, well, maybe I need this design to go 4 times as fast to meet my IO throughput requirements. And I can say, let's unroll this loop by 4. And now I'm going to get 4 hardware multipliers plus some adder logic. So again, just one of the knobs that you can turn in high-level synthesis.
Hey, Mike, we have a quick
Yes,
question. Is the
sure.
architectural exploration achieved through pragma insertion like it's done in Xilinx and AMD?
It is.
Vidas?
It is, yes. Currently, we use pragmas to do things such as loop unrolling and map interface constraints and protocols and things like that. So yes, very similar.
Thanks.
And then lastly, one of the things that we really differ from other HLS tools is that RISE achieves superior Q of R correlation with downstream synthesis. And this is really essential to the next generation of high-level synthesis tools because in the past, high-level synthesis is really good at creating RTL, but then correlating with the backend tools was always problematic. And so what we're doing is we're now essentially able to pull out like the worst case critical paths in the graph before the design has been scheduled in pipeline and optimize those paths and actually crunch them down without changing the fundamental structure of this data flow graph that's being built into RTL. And so we're keeping things high level, but we're getting insights into the downstream tools in order to take advantage of those optimizations. We have the ability to basically run a custom version of Yosis and static timing analysis under the hood to basically get bit level timing, which is really important again for being able to correlate with the downstream RTL. We have adaptive optimizations that essentially will run and do all sorts of low-level RTL optimizations to get better area and timing correlation without reducing this to a bit-level netlist. And then also pipeline and technology mapping. Essentially, it allows us to do technology mapping based on your target technology in order to again get better Q of R, better correlation with downstream synthesis. And that is a quick overview of everything you would like to know about high-level synthesis. Again, we have much more detailed videos that we can provide you with.
Excellent. Okay, thanks, Mike. Tom, you think that you can try to take over the screen? And we'll let
So,
you.
how does that look?
Perfect.
Okay, great. Well, thanks for inviting me to chat here a little bit about Precision Innovations. I'm the CEO, and Precision Innovation develops the first open automated chip design flow based on OpenROAD and built for mass commercialization. We exist to democratize chip design and make chips accessible to every innovator. And our solution is really the only practical solution for AI-driven EDA. So just a little bit about the company. So we were founded in 2019, and we were basically started to work under UCSD to develop OpenROAD when DARPA was funding the development of OpenROAD. And we are what I would call the primary industrial developer. There were many great students doing research, etc., but the team from Precision, a bunch of EDA veterans, was brought in to make sure that we could develop a robust and working tool. We now have about 30 employees and contractors, and the tool is tape out proven, open source. It's a physical design solution that people have used on designs down to 12 nanometer for tape out and down to 2 nanometer and even below that now for estimation. We're working with largest companies that you could imagine and small companies alike, and we can tailor customization features and product support to each company as needed. So you can think of us like the Red Hat SUSE for EDA. So on top of OpenROAD, which is open source, we provide trusted releases, customized development, customized features, accelerated issue resolution, and we're partnered with Rise EDA on that. So they have integrated, as you saw, Yosis, OpenSTA, and later other parts of OpenROAD. And if you needed support, you could turn to us for that kind of support. And our goal is to democratize chip design access to underserved markets, accelerate innovation with machine learning, and provide a cost-effective business model. And we have a very experienced team. So I'm the CEO, Matt Liberty. If you do anything with OpenROAD, you'll see him posting on issues and updating code, etc. Joe Moon is also a long EDA veteran, and we've all worked at all the big EDA companies. Andrew Kong, who really is the grandfather, spiritual leader of OpenROAD, got it started with DARPA back in 2018, is one of our advisors. So AI promises to reinvent chip design. And as part of that, it's exposed a huge bottleneck. Chip designers use AI to generate logic designs. You may use a tool, something like Rise, to generate your RTL logic designs, but you need to evaluate PPA, and that evaluation is becoming a massive bottleneck. So imagine that you have your favorite AI generating thousands of possible RTLs for you to explore. You need a layout and PPA estimator, and the traditional tools are just too slow. On designs that are large, they can run for a very long time, and that also means you need massive compute power and many licenses. Our biggest customers are running 10,000 copies of OpenROAD pretty much all day long. So traditional EDA cost and performance are a roadblock for innovation in this area. So as I mentioned, the proprietary EDA tools were not designed for the AI era. The existing tools can take a long time to run, but designers need overnight or faster results. The AI could want minute results if it could get it. The EDA licenses prevent sharing of scripts and results, blocking industry sharing of research and training sets. If you're going to build an image classifier, you can download a whole bunch of images with data about what they classify to. You can run your algorithm and see if you're better or worse. We don't have anything like that in EDA. And there's no standard format for tool metrics to drive machine learning. Also, teams mix and match tools, and compatibility issues make it hard for people to use vendor-specific offerings. As I mentioned, the estimation can require thousands of parallel running licenses, and each of those can cost 500,000 each. And even our biggest customers tell us they can't afford to spend that much on EDA licenses. And the slow performance, again, means expensive compute usage. So open source revolutionized software development, and it's time for open source EDA. And as you can see, not everything in the stack needs to be open source, but you need to have the key components be open source to unleash innovation. So open source helps us first with adoption. The free unsupported licensing drives adoption in universities, research, and companies. It unlocks a foundation of innovation for commercial use, and also it's training a generation of engineers. And with execution speeds 4 to 20 times faster than the proprietary tools, it allows for fast AI-based estimation. In terms of innovation, the open interfaces, transparent algorithms, if you want to know what the algorithm is, read the code. Modular pipelines let engineers plug into formerly closed flows. And there's also increased security, especially governments care about this for Trojans due to the fact that the code could be inspectable, much the same reason why Linux is very secure. And so this breaks vendor lock-in and creates a faster moving innovation surface for the entire industry. Industry customers need certified releases, so this is an opportunity for precision innovations. Both OpenROAD releases and Foundry PDKs need certification and testing, and Precision has a set of proprietary tests for creating a unique value add. So again, Precision is the Red Hat SUSE of chip design software. You can think of OpenROAD is to Linux as Precision is to Red Hat and SUSE, and we have this AI scalable technology and business model. And really what we want to do is enable hyper-specialized silicon for real-world applications. There are big companies, Apple, Qualcomm, Intel, that are generating processors that everybody's using. But there's a real need for hyper-specialized silicon. One cloud vendor has told us that they expect to have nearly 20 ASICs in each cloud machine that they have, because there are all sorts of specialized applications. And we want to make chip design as iterative and agile as software development. And a tool like Rise has for high-level synthesis helps make that more of a reality. And we can be your trusted partner in leveraging OpenROAD. So let's talk about why using open source for machine learning. First, there's no license cost per run. Now, I don't want you to think that means using the tool is completely free, because there is what I call a productization cost. You have to get it to work in your flow. You have to get it to work with your PDK. There may be something about your specialized design style that needs extra support. So this productization cost, though, can be amortized across usage regardless of scale. So in AI, if you need to run 10,000, 20,000 experiments in parallel to search for the answer that you're looking for, you can do that and you can amortize that cost. You could do that in-house, have your own support. You could pay a company like ours to do it. There's all sorts of options. The fast estimation mode, I think I've talked a lot about, but on average, you'll see 10x faster than proprietary tools. So for a large design, let's say 3-4 million instances, a proprietary tool will run for a week to do what we can do in about a day, which helps you do a lot more experiments in a much shorter time. The license is open source. There's no restrictions on sharing script, so companies can collaborate. You can collaborate freely with universities, whatever makes sense for you. And we have the IEEE Metrics 2.1 standard that you can look up, and that's a format for tool metrics to drive ML. OpenROAD dumps a JSON with those metrics in it, and then that can be read in by a tool trying to optimize and take advantage of those metrics to improve the outcome of the AI. And lastly, I just wanted to mention that we're trying as much as possible to follow the Linux paradigm. So Linux has Linux Foundation, and then you have Red Hat, SUSE, and all sorts of commercial companies. So we started the OpenROAD initiative, which is a public charity for the benefit of open source EDA. You can go to the web source. Andrew Kong and I founded this. And this basically is a neutral organization to control the open source EDA efforts. You decide who has merge control, for example, for your open source code. It owns the trademarks and makes sure everything stays free and open source. It's also a primary goal is to ensure that there is continued development of OpenROAD and expanding to all open source EDA as that expands. We can also work on developing open source PDKs, both manufacturable and proxy, like ASAP7. So the project model is that project teams will be formed to drive initiatives. And we also have some funding from the US National Science Foundation to promote the ecosystem. And you can read about that at the link on the presentation. So
Tom,
thank you
we have
very
a
much.
quick question here that I
Oh,
think
sure.
we have time to answer. Any good source of documentation for OpenROAD? I'm using OpenLane underneath, uses OpenROAD, but frankly, missing good documentation to explore in detail, be in ICC2 and Innovis user.
Yeah, sure. There's a read the docs page. So if you just type into Google OpenROAD read the docs, all the documentation is right there, from installation guide to manuals.
Okay. And then another quick one is the slow run, maybe this is an opinion piece, is the slow run a
Yes.
proprietary tool attributed to old legacy code, which is not the case in OpenROAD for newly developed code base?
Certainly that's part of it. A lot of the OpenROAD code is new and it's faster, but part of it is also the philosophy behind it, which is it doesn't invoke the expensive algorithms unless it really needs to finalize the chip.
Yeah. Okay. Super. All
Okay.
right.
Well, thank you.
Thank you very much. Alan, are you ready to take
Yeah,
over? Okay.
see if we do this right. Do you see?
We see you've still got your little, yep, there you go. So you've
Okay,
got your screen and then
perfect.
stuff in the middle. Perfect.
Perfect. Hey, so let's talk a little bit about design space exploration in a practical term. So we already, Mike outlined how you could change the shape of a design, explore parallelism and so forth. And that's of course super important, but how do you really do a black box search in a design space? We have a tool chain that enable that based on metrics. As Tom outlined, you certainly want to make sure that you do your place and route estimations early up front. You don't want late surprises. We like to believe, and we see that we can certainly do optimization and explore the perfect setup early in a design space as we are defining architectures, but we certainly want to use tools like OpenROAD that we have integrated fully with all the nice metrics and flow structure that Tom and team have created over the years, such that you can really go from a behavioral, almost like a specification, into the physical domain to convert about to that Paleo font that you're really searching for. Might it be parallelism, throughput, area constraints, whatever you are searching for. Any metrics that exist from high-level synthesis, RTL, to place and route, can be used as a goal and an objective. I would like to share a little bit about how that is done in the most practical term. The example I will walk through is a small example. Of course, you can do big examples, and we will sit and wait for place and route to finish and so forth. So I'm taking a very small design to show the principles, and these principles will scale to any degree that you can imagine. The whole idea is that the toolchain we have has all the phases that you will typically go through, such as you start with a behavioral simulation, you start to optimize, you do high-level synthesis, you do verification, you might do verification of the RTL that you're creating against your original reference implementation. You may need to have some statistics and quality of result metrics. You may need to compare against different versions of the same design. You have one design that looks like this, one design that looks like that, because it's more parallel. You may want to have more details. You may want to run a toolchain like yours to get place and route or other commercial EDA tools. You may want to have place and route, as Tom said, OpenROAD for estimation. You might even have a design space exploration tool exploring itself. All of that can be done. I'd like to show you how it's done. Again, it's a small example, but it shows the principle. Here's a fur filter. It came from a specification. We used a tool to create it. And as Mike outlined, the details here is mainly around, and the important part is really more about the loop unrolling. As Mike said, as you unroll a loop, then you get more area and you get faster throughput and so forth. So in our example, the way that we have architected the RISE toolchain is that the interface through this flow is a simple command line argument. This is a Python flow that has a shallow shell around it, so it's easy to control from any toolchain. All outputs are visible metric JSON structures, just like Tom outlined, and therefore machine readable, human readable. Everything is predictable. Everything is showing the metrics results. And because of that, you can start to imagine that you can now get a machine to make decisions on what should be done. The input, as I said, is a simple design. The way we set up our toolchain is quite uneventful. It defines the design. What is my target technology? What are you hoping to aim at? What happens if you cannot meet timing? What is my test bench? What is the definition of a pass-fail in a test bench environment? How should we run the tool? Once you run the tool, it's again very simple. RDA builder, flag file, this file, and we run. What's happening is we are now synthesizing the design, the fur filters we talked about with interfaces and loop unrolling in some standard form. We optimize the design, we do optimization, we do synthesis. Look at these runtimes. We do verification. So verification here is on the critical runtime. It takes a few seconds to build the design. To do functional verification takes a little bit longer. And we get some metrics. These metrics are gathered from everything that has been generated, just like what Tom outlined. And this is simply just from the high-level synthesis to the RTL that got created. We get some throughput numbers, we get some compute cycles, we have latencies, we have some estimation of number of flip-flops, the exact number of flip-flops, the estimated area as the tool see it, and we might say, ooh, that's complicated. I like the throughput, but I'm concerned about the area. As we outlined, we can control this loop unrolling by simply, it's a define, as you can see, you might see. It is a define, so we can create the exact same design, and we actually like to have a define. And we like to set this guy We like to not do loop unrolling. Here it's fully unrolled, so it's a fast design and therefore replicated many times. Or we could do the loop unrolling with such that it's condensed design. We could also look at
Hey,
how is
Ellen,
it, yeah,
I have one quick thing that you might want to add to it, which is wouldn't use reinforced learning and exploration require a lot of steps, hundreds of thousands, if not millions? If so, wouldn't running such a number of high-level synthesis, logic synthesis, and PNR take a large amount of time? That's basically unfeasible. So maybe,
if you want it by end, let me show you. If you want,
because I think that's really the kind of one of the big questions, right?
yeah,
Is how much of this is feasible?
but it makes little sense to optimize PNR down here if you can start to early explore what might be a good architecture.
Right.
So you want to start early on, do lots of iterations. We just saw runtimes are measured in seconds. Most machines has number of cores, so you can do a lot of exploration in the space. In these worlds, and we are not talking about design space exploration yet, we're just defining the space we're searching in. In this space, it's the number of loop unrolls, right, times clock frequency. But the whole idea with design space exploration is you want to do it early, and as you're starting to figure out what might be the shape of the architecture you're looking at, then you want to add more details, more fidelity.
Right. So you don't do full PNR on all of them. You basically are exploring at the top first and then beginning to add more fidelity. Yeah.
Yeah, you absolutely could, but most people want to make sure that they are happy with the architecture before they start to add more fidelity, right?
Yep.
And that's why the correlation is so important, that you don't
Yes.
get any surprises.
Yep. Thank you.
Of course. So if you look at the run we just did, we can take a look of the analysis on what was really created. We have an op summary. We see we have so many multipliers. It uses quite a lot of area. So we can take a look at all kinds of things. We can look at how the pipelines are created, where things are coming from, etc. But in this example, we simply just want to make sure we understand what is it that this area is now for multipliers. But if the design objective is having a specific throughput, what might be that throughput? So we could run the exact same design where we're setting a define to not do the loop unrolling. We will therefore get a very compact design. And again, we are still at the high level phase. We're not adding place about at this point in time. We're waiting for verification to run. And now we have a much, much slower design. You might recall the throughput before was 1, and the compute cycle, so the time it takes to conclude, is now too slow, but the size might be right. So the challenge is, how on earth would you go and find the right parameter sets for controlling the loop to get a throughput of, for example, 6 or below 6? And this is where design space exploration comes in. Let me show you how that is working. So for us, we have this notion of flag files, and flag files, as I said, is a command line setting. So if you have a comment set up for a study, which is this notion of defining the design space, you define what might be the study, you define what is adaptive optimization. So we don't want any surprises later on. We want to use this incremental synthesis tool to make sure the critical path is being optimized correctly, so we don't get a big swing and cannot trust the estimation of the tool. We define a study, we wiggle this define we just saw can go from one dimension to another. We define flags we want to run, and we give it some names. And all metrics that exist, just like Tom said, all metrics that exist at each of the different phases, slag, area, RTL, if we add RTL synthesis tool, place and route, etc., all of them are available for the engine to go and search for and do input parameter search. So if we have a base set up for the configuration, in the study objective, so the goal of this study, we can define what is it really I want to search for. In this example, I would like to control my objective is to have a clock frequency for the design, clock to be under 2,000 picoseconds. I want my area under something. I want my throughput under something, but I don't want to run more than 4 minutes, and I don't want more than 44 trials. There was a question about the space. The longer you run, the more precise picturable you get of that space. So it's this balance act on what might really be the right trade-off before you really start to see reinforced learning to kicking as it's getting applied. But let me run it and we take a look. Again, just like before. And it was called design space, high level. Now it runs. It creates a study. The study will create studies, trials, and it will run n number up to 44 instances of itself. And it will start to converge. We can use a tool to look at the study and see how it behaves. As we are running, the web interface for the study mechanism, it tells us what's running, what is being converged, and we can let it run a little bit longer. And I show you how it's done. Any questions? What is running?
There was one that Mike started to answer, but I don't know if you want to interactively also answer it, which is there a way to switch between LLM and HLS software if we want optimized algorithm? And Mike was, we support most LLMs,
Yeah.
but is there anything else you want to add with any of that? Okay.
No. So in this example, we can see we're starting to build data points of the Polaro front. So this is where, as soon as we start to change the behavior of one of these points, then we will get a worse Q of R, which is, we were hoping to get a throughput of 6 in this example. Still running, and eventually it will be done. And again, we're running 44 instances of the tool in batches of 8. There's a mechanism on how often you get reinforced learning information, and that's depend on the design size that you're working with. Let's see if we are there. We're still running. We see the trials, what was found, how it was ran, when it was run, what are the best trials. We see the metrics being propagated back. And I think we're very close to be done. It's like watching paint dry. But again, it's 44 instances as a run, and we're starting to see a trend that we get a front where we can run at a certain frequency, and we have a throughput seems to be around 6, 7. You see that it's all, our front is down here. And now all runs have been run. We maxed out at 44, and here's our front in textual form, right? So in a couple of minutes, we were running 44 runs, and we got the front being set up. And that's obviously nice. But what you do when you want to make sure that you don't get any surprises at place and route, and this is where the integration with OpenROAD is so invaluable. OpenROAD for us is extremely easy. Actually, let me just run it, and you see it live. I now already have the study, and I could do endless analysis, but I would like to start this so you can see the integration, how well designed OpenROAD is. OpenROAD for us is encapsulated in a Docker, and it makes it very easy to run. We set up the number of threads. We stop at certain places at place and route. We can do CTS, you could do routing. There's some flags and how do you auto size the die, etc. All of this can be done placed into C. As you're going to run, or as we are going to run, we will eventually start to have a runner that runs OpenROAD in the Docker environment. It uses make. If you use the OpenROAD toolchain, you will this is a flow that is normal. So you run make in the Docker environment, you get the number of cores, you stop at place, create the make file, which is the primary API into OpenROAD, build the timing constraints. We already know what the clock is. We know what the design is. We now start to see OpenROAD working. And this is for estimation. And in a couple of minutes, you take this version of the design, this version of the design, and you automatically turn that into a place and routable estimated design, which I think is quite something. If you work with place and route tools in the past, this is not normal that you just automate it. One of the things that is key important for these tool chains is the correlation. So if we look at the area correlation, just under 2000, just under 2000, just under 2000, very little swing. So we don't get this massive, the tools didn't agree on area. And in terms of the performance, also quite in agreement. In this case, we are using YOSYS as the place of the RTL synthesis engine, and YOSYS, just like other tools, are easy to integrate. It will generate the TICL files, the drivers for YOSYS. You have the YOSYS metrics, you have YOSYS log, just like we're used to. Everything is completely modular and easy to use. You could then imagine, well, why wouldn't I just go, as somebody was asking, and do a full state OpenROAD exploration? And of course you can do that. We set up the file, we have a common design space exploration, but in this example, we would like to go and search for not the output metrics at high-level synthesis, but the output metrics at place and route. We want to search for the throughput where the clock and the area are within our constraints. So if we look at our slides for before, we are now looking at the metrics at this point in time compared to before we were looking at this point in time. And that, of course, takes some time. As another TV kitchen, I did rerun this because it takes around half an hour or so. Let me show you. And then in comparison, this was the study we just did. We have some one-time statistics. You see that? We started it, it ran, and here's all our trials and the times it takes. A couple of minutes, yeah? If I do the one where we just do RTL, I ran that yesterday. It ran from, again, 44 different instances of the same design, but metrics for RTL. It ran in 20 minutes. What I find mind-blowing is I did the same thing last night from OpenROAD. In 20 minutes, I did 22 samples of place and route, auto-placed with statistics that is correlating just as well as you just saw. What this gives me the ability to do is to trust the tool chain such that when I say early on that it's about right for a high-level synthesis tool, I can, of course, look into different metrics as I have more and more fidelity, as I'm progressing down the details of as I get closer and closer to silicon. Super simple to integrate, and kudos for Tom and his team to create a tool chain that is so fast, so easy to use, and we can run as many instances as we have compute and memory for. I find it very, very, very easy to use and integrate. Mike, anything to add?
Well, there's a question, and I think that's a good one that we could discuss. The question is, I use Xilinx AMD Vitis HLS tool for FPGA designs. I've observed that sometimes the results, such as achieved clock frequency after PNR, can be very different from the results after C synthesis. Would this also happen in your tool? If so, I guess the DSC results could be misleading if such discrepancy exists.
True. If the further, it's just like with life. The more you know, the more accurate it will be. That's just how it is. But because of this adaptive optimization, we are applying the swings that you're seeing are very small. You will see a swing. Whereas Ellie talked about, it's within 10, 20%, which I think is acceptable. You are not seeing the 400% or the 5x totally off, so you cannot trust it at all. the further and the more fidelity you add, the more precise it will be. I think as you go and do the architecture exploration, you probably don't need to run place and route, but as you're getting into the details of maybe memory structures and the routing conjecture aspects of a place and route, you want to make sure that you add tools like OpenROAD to the estimation. It depends on the question in hand.
I mean, you'll get the right. So you've got to get the RTL right, but if you're doing BIDIS, if you're targeting an FPGA, then
Right.
this doesn't really, the back end doesn't really apply as much here. You'd have to use the
Yeah.
Xilinx tools.
The one thing I'll comment on that is it applies in that the same type of routing issues that typically create problems in FPGA, which would be routing to block RAMs or routing to DSP blocks. You can have similar effects in ASIC place and route. And one of the things I see happening, since we've already closed the loop, we have a closed loop flow with running Yosis under the hood that gives us very precise timing estimates at the RTL level. We will do the same thing with place and route. It's simply a matter of understanding how to back annotate that information so we can then turn some knobs in the HLS tool. And the OpenROAD PNR is ideal for this because it's so much faster than some of the other tools that you really can do real exploration.
And automate it. I mean, think about this is the API. You don't get simpler than that. And then Tom and team takes care of all the automation around it. It's quite something.
Okay. Any other questions? All right. Oh, that's cool. Yeah, so I think that there's a lot here that we've done to integrate. Basically we've plugged in OpenROAD, but we can plug in all sorts of other tools too. This interface and this exploration loop is very open, and we're very open with our IR, very open with all of the formats that we've been using. None of that is closed and hidden, right? So we think that this is also really good for folks out there doing research and trying to understand different architectures. So ahead and share my slide. Okay, so I'll do a quick wrap up and then I will open it up for Q&A. So I wanted to thank everybody. We've kind of gotten through the main sections of the presentation. Really, in summary, we have RISE, which is the next generation of high-level design, and really the next generation in both the speed and, more importantly, as you've seen in the Q of R, right, to get high quality, meet the PPA, and make it predictable to your production level silicon and synthesis tools in a fraction of the time. Working tightly with Precision and OpenROAD to basically that next level of iteration, right? So as you choose the ones that you'd like to have further fidelity in, as Alan talked about, to make sure that that you have the fast, correlated, and economical physical estimation metrics, so that as you kind of add more data to your flow, that you can see that is. And all of this with all of the metrics, they're very open. You can have all of these metrics in our AI flow, in your own AI flow, however you want to do it. And then the two of them together really enabling a true shift left with this AI guided exploration. And we'll continue to have more information and more webinars on the different things that you could do within our AI solution. Okay. Thank you so much for attending. We really appreciate all your coming, and please let us know if you have questions. I'll send out the recording in a little bit, and thank you very much.